All right, today we're going to be looking at section 5.2, definite integrals. Before now, we were trying to find the area under a curve and focusing on the positive result, but sometimes those functions do go below the x-axis. So we are now looking at finding the net area. So that's the part above the x-axis, bounded by the curve in the x-axis, and then the part below. When it goes below, this will be considered negative area. And this example is showing the midpoint, finding the areas of those rectangles and giving you a negative sum. And so whenever we go a little bit deeper, we're going to start talking about net area, where we have a positive area above and then maybe some negative area below. Here is again a left Riemann sum, giving you an illustration of we have area above the graph and area below. Going over Riemann sum and the partition. And then we give a formal definition of net area. It says consider region R bounded by the graph of a continuous function f and the x-axis between some point A and B. The net area R is the sum of the areas of R that lie above the x-axis, and then minus the sum of the areas of the parts of R that lie below. So the blue above, you would add those, and then you would subtract what's below in red. Then it goes over definition of integral. So again, this is the net area, and this is saying the limit. So we've talked about limits, but we're going to take this sum and we can make, 5 partitions, 10 partitions, but we're going to make as many rectangles as we can. And the limit of this function is what we're going to be calling the net area. And it's going to kind of walk us into the definition of an integral. So as you can see, just a couple rectangles here, a couple here, based on the partitions. But here we start making more, smaller and smaller. It gets more to compute, but there's 40. Then down here we go to 75 subintervals. And then here we've gone to infinity. So as n goes to infinity, the change in x is so small it goes to 0. So you pretty much get the whole area. And this is just a general sum, general idea, general partition as we kind of transition from Riemann sums to the integral. So here's that definition here, just a general sum definition. Then we transition to the definition of an integral. So you have a function f defined on AB. It says if the limit as the change in x goes to 0, so that's making as many partitions as we can, of this sum exists and is unique of all partitions, and all choices of k, xk star. This limit is the definition of the integral from a to b, and we write it like this. So this little symbol is an integral. So the integral from a to b of f of x dx is equal to the limit as x goes to 0 of the sum from k equals 1 to n of the function. This is kind of going over some notation of the integral and the explanation right here. You have an upper limit, a lower limit, the integrand, and then you have a lower limit of the summation, upper limit, and you have your function. So it's kind of comparing the two and showing you a relationship between them. Sometimes we might denote it with different variables, but 3 different scenarios, exact same graph. The functions look different with the notation, fx, fw, fs, and that's just the labeling of the x-axis. But as you see, all 3 are equal. They're exactly the same, so don't let the change of variables confuse you. Here we talk about a little bit more of the definition of evaluating integrals. Here's a theorem. F is continuous on AB, bounded on AB with a finite number of discontinuities. F is integrable on AB. Here are some examples. and some visuals that you can kind of see. They're doing the sum of these three different parts, positive, a negative, a positive. Here's the solution down below for the net area. Another example, okay? And then I want you to solve these examples using geometry. A lot of examples you get to kind of see and kind of walk through. So here's one with example, looks like a trapezoid, so you find the area of the trapezoid, and they're showing that here. Here we have two triangles. Here we got a circle, so we do a fourth of a circle and find that area. Again, we got a few more examples, definite integrals from graphs, some visuals to see and walk through. All of these are good to kind of read through and see if you get a better understanding. Then we start talking about properties of integrals. So we have integral from b to a. So normally b is our upper limit, and it's saying that here a is less than b. So if we have it backwards, the upper limit at the bottom and then the lower limit at the top, that is the same as just doing the negative of it, the opposite, and then reversing your limits, a to b, f of x dx. So again, it's saying reversing the limits. If your upper and lower endpoint are flipped, you can reverse it and just do the negative of that integral. If you go from point to point, that is 0 from the same point. We have integral of a sum. You can split it up. The integral of a sum is the sum of those two integrals separated. And then here's proving that property. And then we have constants in the integral. So you have some multiple c times the integral. You can pull that constant out and then do the integral and just multiply times c. And then here are again some of the steps showing that. You can do subintervals. So again, this is kind of like adding two intervals together, this piece and this piece, when they're a little bit different. Integrals of absolute values. So you can kind of see how this shape went below the x-axis and we just did the positive of it. So again, just kind of walks you through this using the table. We also have some more properties listed. So again, integral at a fixed point is 0 because there's no width to get the area. Changing the limits, lower limit and upper limit, you can flip those and do the negative of the integral. You can add or subtract integrals, similar formula. Whether you add them together or subtract them, you can separate the integration. When you have a constant, you can pull that constant out as a multiple. And then you can do partitions of limits. So instead of going all the way from a to b, you can go from a to some point p in between, and then start again from some point p to b. And sometimes that makes it a little bit easier to evaluate. Again, these are just some examples going over properties of integrals, some bounds on definite integrals, properties, and then some more visuals. So bounds, like it's between 2 points. This is kind of where we're doing the upper bound and the lower bound of the function to help us figure out the integral. And then again, some additional properties when bounding the integral. So a to b, that's going to be greater than 0. We can say this integral is greater than some other function, and the integral will be greater than that. And then if one function is less than the other, then when we integrate it, that function will be less than the other, based on bounds. And then here we are evaluating integrals using limits. So again, as the change in x goes to 0, so as I make as many rectangles as I can, and I add them all up, the integral is equal to that. And so they show a few examples using definite integrals for evaluating So these are all good, kind of using Riemann sums to kind of walk through, see these examples, and then I will be doing these in my math lab. So just a general overview. We'll learn a little bit more about integrals later, but this is just kind of walking us or getting us into the beginning of it.